Ladies and gentlemen, you can see an artist's view from the late 1970s on seafloor mining, and this is still the imagination and perception of many concerns. This talk summarizes the different developments and attempts on mining polymetallic metal sulfides from the ocean floor and presents a concept for vertical, lower impact and more sustained oil recovery. You will note that the sulfide mining on this artist's drawing already points to vertical techniques with respect to sulfide mining. The traditional concept all involved driving vehicles on the seafloor independent of the type of mineralization, ores, or the mode of occurrence. Mining concepts are similar for loose nodules, intergrown crust, subsurface sulfides. The concepts also suggest vertical riser technology with the use of seawater slurry pumps for the transportation onto the production vessel and the release of the transport medium at depth. Mining polymetallic sulfides from seafloor subsurface necessarily will involve mining activities towards depth. As a consequence, and similar to land-based deposits, an open-pit mining concept was adopted, as shown in the slide before and followed by Nautilus for its Solvara deposit in Papua New Guinea. However, an alternative concept of a vertical recovery system was developed by German Prusak already in the late 70s. For the recovery of sulfide muds from the Red Sea. Both concepts included the discharge of transport and processed water to the ocean. Prusak's vertical recovery system involved the use of a suction head, a number of positioning, measuring, and analyzing instruments, electric, flushing, water, and mining pumps, as well as ore processing on the mining vessel, including the discharge of tailings from the vessel to surface water. The joint activities by Saudi Arabia, Sudan, and Germany in the Atlantis too deep in the Red Sea in between 1977 and 1981 was based on numerous sediment corings for exploration. Projects towards a pre-pilot mining test, PPMT, included the developments of the suction head and the riser. The PPMT was performed in 1979 at a depth of 2,200 meters and recovered 5,000 cubic meters of sulfide mud, which were processed on the production vessel already. The Nautilus activities involved activities after the first findings of sulfides in a back arc environment in 1990 by a German university and subsequent research by Australia's CSIRO. Nautilus licensed the area in 1997 and started exploration activities in 2005, followed by an open pit mining strategy and the design of appropriate mining machines, including continuous miner, wire cutter, collecting machines, and lift pumps. The mining strategy largely followed the old concept of moving vehicles in the deposit area, the excavation of the surface ore and host rocks, and development towards depth. Given the limited size of metal sulfide deposits on surface, which is on average less than 300 meters in diameter, open pit mining requires tremendous amount of excavation and removal of less mineralized or even volcanic rocks, which not only will cause large tailing clouds at the surrounding seafloor, but also increase production costs immensely. Processed water from the riser will be discharged close to the seafloor. The funnel shape and the need for a number of umbilicals for different mining tools, plus the riser, likely create spatial problems in a limited area. The discharge of processed water may result in limited visibility during the mining process. JOGMEC from Japan performed the world's first ore lifting pilot test for polymetallic sulfides in August and September 2017 at a water depth of about 1,600 meters within the Okinawa Trough. JOGMEC's concept was similar to that of Nautilus. However, the Japanese pilot mining test was carried out as a multi-ship operation. The various connecting devices like riser and umbilicals from the seafloor to the sea surface are linked to two different vessels, one controlling the mining device and the other one taking up the recovered material via the riser system. This limits the danger of an umbilical. A third vessel is addressed as a carrier for lifted seawater. A reservoir concept was established to control a constant flow in the umbilical, potentially by airlift. Environmental monitoring devices are installed. The tested excavator and ore collector represented a downsized model of the conceptual mining tool. Economic studies foresee a required daily production of about 5,000 tons of metal sulfides. During the test, a total of 16 tons of material, including sulfide ore, was raised onto the ore lifting support vessel. The vessel setup was tested following the mining concept. So what other mining concepts are available? As I already pointed out, Prusak designed a vertical concept for the recovery of metalliferous mads in the Red Sea, and available techniques can possibly accommodate the particular shape of narrow, three-dimensional and conical geological bodies better than the traditional open-pit mining technique developed for land-based deposits. Seafloor massive sulfides deposits are considered three-dimensional, conical funnel shape, and they are usually narrowing towards the base. The deeper portions of the deposits are considered high temperature and therefore copper gold rich, as can be seen in the fossil equivalents on land, which are mined on land. What advantages could vertical mining have? It is selective and diminishes the recovery of barren rock or pyrite ore of no use. Efficiency and feasibility of mining could be improved, especially as proven and tested trench cutter technology exists and can be used. The concept includes separation of process water during the mining, and the mining process could be continuous or discontinuous. This may all lead to a lower environmental footprint. Trench cutter operations were already in place for diamond exploration. The drilling and trench cutter operations are standard in offshore diamond exploration and exploitation since 1994. Different sizes and compositions of alluvial gravel are released from the seafloor with closely defined grain sizes to allow for safe diamond recovery for water depth down to 200 meters. Trench cutting has a long tradition in diamond exploration. The kimberlite diamond host rocks represent volcanic diatribes with a conical funnel shape close to surface, very similar to metal sulfide deposits on the ocean floor. Exploration was widely performed in Canada's north, for example, in the Ikati mine in 2003, as you can see on the left-hand side. Recent exploration in central Saskatchewan on Rio Tinto's Orient South Diamond project included a total of 2,351 meters of trench cutter drilling and recovered a total of 6,800 cubic meters from depth down to 251 meters with defined particle sizes between 0.85 to 80 millimeters. The reason for this was that Rio Tinto did not want to have the diamonds cut down to smaller sizes. They want the big one. Trench cutting is selective, so it allows for very selective and low impact drilling. It was used in big cities, for example, in the Louvre Gardens, as you can see on this slide, in downtown Paris, or beside the Natural History Museum in Vienna. Footprints are usually about 1.5 by 3.2 meters, as you can see on the slide. So, as shown before, most of the necessary equipment for the vertical approach and trench cutter concept recovering metal sulfides from the seafloor already exists and has been tested. However, a test in deeper seawater is missing, but planned in VGR's contract area in 2023. The test includes a heavy lifting vessel equipped with cranes and winches and the necessary deck space for the trench cutter device and necessary equipment with auxiliary parts and offering the storage capacity for the recovered sulfide ore. An umbilical winch with a 3,000 meters deep sea cable, world-class remotely operated vehicles for the handling of rigging, servicing and monitoring in the deep sea, and other auxiliary equipment, for example, control container and hydraulic power packs are readily available on the market. The collector bucket sits on top of the trench cutter template with 3 stabilizing legs. The purpose of the template is to guide and level the trench cutter in uneven terrain and to hold the power pack for energy supply for the cutting operation. A protection collar around the cutter wheels prevents fine sediments from forming plumes in the seawater. All cutting chips are conveyed towards the suction inlet of the cutter pump, and all particles smaller than 75 millimeters are pumped into the collector bucket. Within the ore collector bucket, an integrated separation unit separates solids from seawater. The ore cuttings settle in the bucket, whereas the seawater will be pumped back to the trench cutter where it will be reused as a transport medium for the cuttings. The trench cutter has a footprint of 1.5 by 3.2 meters, as I mentioned before, and a weight of up to 150 tons. The current cutting depth is planned for 8 meters. Therefore, one cut will extract approximately 40 cubic meters of ore. The collector is designed to hold 100 tons of ore before it is recovered onto the vessel. First testing will be closely monitored by the contractor BGR. Thank you for your attention.